Okay, so let's continue. So there is a point in the chat. I think there's typo for the sign of 7. No. Okay, so before the break, we looked at discriminant functions, right? Like, so very simple discriminant function, which is W transpose X plus W0. Like, we talked about how the bias term, like, is kind of acting like a threshold, right? Okay, so now let's try to understand a bit more about the decision surface. Okay, to do that, okay, so to do that, let's consider there are two features, x1 and x2. Okay, which means my decision surface is going to be 1D, right? So 2 minus 1. So it could be any line that you're drawing, right? So let's say this is my decision surface, just as an example. Okay, so y is equal to 0. Okay, this is the region where y is greater than 0, region 1. Okay, and this is the region where y is less than 0. Let's call it class 2, region 2. Is it clear? Okay, so now let's consider any 2 points, xa and xb. Okay, so they both lie on the decision surface. Okay, so if I tell you xa lies on the decision surface, then what is y of xa? 0, right? Similarly, y of xb is also going to be 0, right? Or in other words, W transpose XA plus W0, which is what the y function is going to be 0, and W transpose XA, sorry, XB plus W0 is also going to be 0, right? Now I can combine these two things. So W transpose XA plus W0 plus, sorry, is equal to W transpose XB W0 plus W0, right? They are both equal to 0. Now the plus W0 cancels. So what I have is W transpose XA is equal to W transpose XB, or in other words, W transpose times XA minus XB is equal to 0. Okay, is that clear? Okay, now I told you that XA and XB are any 2 points in the decision surface, right? So let us consider this to be XA and this to be XB. Okay, now XA minus XB is basically the line, right? So the line, it's a line equation for the decision surface. Like XA minus XB is the line represent, like line where XA and XB lies together, right? So now I tell you that the W transpose XA minus XB is equal to 0. So what is the geometric interpretation for that? It says that W matrix, that the W vector is orthogonal to this line, right? So when I say W transpose something is equal to 0, then it means they are both orthogonal. So, or in other words, my W matrix, right? So it will always be perpendicular to my decision surface. Okay, now this is my W. Now, if you continue this line, you will see that this is 90 degree. Is that clear? So, or in other words, the W vector determines the orientation of the decision surface. Okay, so if I have a different W vector, if I tell you this is the W vector, now by just based on this fact, you can tell me what is the orientation of the decision surface. My decision surface is going to be like perpendicular to this line, right? So it could be either this, or it could be this, or it could be this. That we don't know. But what we know is this is the direction for my decision surface. Is that clear? So now that is the contribution of the W vector. So the W vector, to summarize the first point, the W vector, right? It determines the orientation of the decision surface. Is that clear? Now we want to understand, like, okay, so W tells us the direction, but where do I place this vector, right? So who is going to decide where to keep this vector, right? Like, is this my decision surface, or is this my decision surface, or is this my decision surface? Can someone answer even without equations? So what do you think will determine the location? W0, right? Because there are only two elements here. There is W and W0. W tells you what is the direction. Then W0, like just like a thresholding function, tells you what is the distance. Okay. So let me again prove that. So now we are going to consider the same diagram. Okay. So you have x1 and x2, and you have this function which is y is equal to 0, right? And you have this W. Okay. So now let's consider where this W vector will meet the decision surface. Like you just extend this. So this is where it meets, right? So we are going to call this as x dash. So x dash is the point in my decision surface which is perpendicular to W. Okay. Now when I say it is perpendicular to W, then it just means that x dash is equal to some alpha times W, right? So you can rescale W with some value alpha for some scalar alpha, okay? And you are going to reach the x dash, right? Like for example, it could be the case that 1.5 times W you touch the decision surface, or 1.7 times W you touch the decision surface, okay? Now, we know that x dash is on the decision surface. So that means that y of x dash is going to be 0, right? Or in other words, W transpose x dash plus W0 is going to be 0, okay? And we already know that x dash is alpha times W. So alpha times W transpose W plus W0 is going to be 0, okay? Now alpha is going to be minus W divided by W transpose W, okay? Now W transpose W is just the L2 norm of W, right? So alpha is given by minus W0 divided by this. Okay, now I have found the scaling factor. Okay, so now we can compute the distance x dash. So the distance from x dash to the origin is given by nothing but this, right? Like, so what is the norm of this vector x dash? So which is nothing but alpha W or alpha times W. Is that clear? So now I can substitute alpha value, okay? So let me go to the next page. So this is going to be alpha times W. We know that alpha is basically minus W0 by this square, right? So this becomes minus W0 by this. Okay. So or in other words, W0 is the one which is determining the location of the decision function. Okay, so if I go back to this picture, okay, now this distance, right, the distance from origin to the decision surface, this is guided by minus W0 by norm of W. Is that clear? Okay, so now I think I have established two observations. What is the first observation? The first observation is W of the discriminant function is what is deciding the direction, and the W0 is deciding the distance. Okay. Now there is just one last thing. Okay, so the last thing is, given any data point, okay, let's just say X, okay, you compute Y is equal to, like, you compute Y of X, which is W transpose X plus W0, right? Now you get a number, right? Now what does that number signify? Because that is not the class value, right? So like, what is the significance of that number? So for example, I do Y of X and I get 7. And I do Y of X again, like with a different X, I get minus 2. Or sometimes I get plus 10, okay? Now what does that number signify? Okay, so to understand that, let's consider any arbitrary point X. Okay, now again I'm going to draw the same diagram. Maybe let me see if I can copy the diagram without affecting the recording. Okay, so this Part-3, paste. Okay, let's see if it works. Okay, now let's consider any point. Okay, so I'm going to consider a point like this. This is some X. Okay, now this X gives me this value, and I know that this is in region 1, right? So if it is in region 1, it is class 1. That we know already, right? So we know that if this X lies here, then it is going to be class 1. But is there any significance about how far they are from the boundary, right? Like, so to do that, let us consider the orthogonal projection of this vector to the decision surface. Okay, so this is 90 degree. Okay, so now we are going to call this vector the vector which this data point here, right? So we are going to call this as X perpendicular. Okay, so now I can write the equation of X. Equation of X is equal to X perpendicular. Okay, so this is my X equation, right? This is X perpendicular. Now by basic geometry, X, this vector X is basically sum of this vector and this vector, right? So this vector is given by X perpendicular. So what is this vector, this part? So this part kind of looks like W, right? So they are in the same direction. This looks exactly like, this is in the same direction as W, but it is going to have different scale, right? So we can just call that as R times W by W. Okay, now we just need to find what is this R. So that R is what is deciding how far is this thing from the how far it is from the decision surface, right? So to do that, it's a very simple algebra here. So I'm going to multiply all these terms by W. So this becomes W transpose X is equal to W transpose X perpendicular plus R times W transpose W by this. Okay, I'm going to add W0 in both the sides. So this becomes W transpose X plus W0 plus equal to W transpose X perpendicular plus W0 plus R times W transpose W by this. I'm adding once. Now you can realize that this is nothing but Y of X is equal to, this is nothing but Y of x perpendicular plus r times w transpose w by w, right? So y of x is some number. We don't know what that number is, but we know what is y of x perpendicular. So what is y of x perpendicular? I'll show you where is x. So x is here. So what is y of x perpendicular? 0, right? So this is 0 plus r times. So what you have in the top is w square, right? So there's one w below, like, so it just becomes w. Okay, so now r is y of x divided by norm of w. Is that clear? So, or in other words, this gap is nothing but y of x by norm of w. So the sign of this r, whether it is like in the top or bottom, right? That is going to tell you which class this x belongs to, and the magnitude of this thing is going to tell you how far it is from the decision surface. Is that clear? So now I think there are 3 important properties that we have discussed. Let me summarize. First of all, the decision surface is going to be perpendicular to W. Okay? And second of all, the displacement of decision surface, right, is controlled by the bias W0. Okay? And third of all, the signed orthogonal distance of a general point x from the decision surface is given by y of x by w. Is that clear? So we are going to make use of these properties when we design algorithms. Like, so that's why we see these properties now. Okay. Now let's extend our discussion to multi-class problems. Okay. So far we discussed everything for 2 classes, right? Like, now what happens if I have multiple classes? Multiple classes. Okay. So when I have multiple classes, how do I extend this idea of scoring function or determinant function, right? So now there are many options here actually. Okay, so we will talk about all of them and their like plus and minus. So the first option that we have is the idea of one versus rest classifier. Okay, so if you have k classes to consider, you're going to consider k minus classifiers, each focusing on one of the classes. So there will be one class. Okay, so let's say there are 4 or 5 classes. Okay, so the idea is to construct 4 classifiers. The first classifier will classify whether something is 1 or not 1. The second classifier will classify everything as 2 or not 2. Then 3 or not 3, 4 or not 4. If you have a not 1, 2, 3, 4, then it is automatically 5. Right? So in this case, the idea is to design k minus 1 classifiers. You have k minus 1 2 class problems, which is going to model this k class problem. Okay. Now, let's consider 3 classes. Okay. Now in 3 classes, let's say this is for class 1. So this side is class 1, this side is not class 1. Okay. Now I might have another classifier, okay, which is going to tell this is class 2 and this is not class 2. Okay. So now this is region 1, so the region of the class 1. So this is region 2. Anything which is not class 1 and class 2 is class 3, right? So this is my region 3. So clear? Now this classifier has some trouble region. Okay, so you think about this particular place. Now in this place, the data is classified as both class 1 and class 2. So both the classifier says, oh, this is class 1 and this is class 2, right? So now it is not very clear which class it belongs to, right? So that's the problem with if you go with one versus rest. Okay, you can have situation where you don't know what class. It could be either of the classes. Okay, now there is an alternate approach for this. Okay, so which is the idea of one versus one classifier. Okay, so in one versus one classifier, if you have 5 classes, you're going to consider one classifier for 1 versus 2, 1 versus 3, 1 versus 4, 1 versus 5. There are 4 classifiers. Then you consider classifiers for 2 versus 3, 2 versus 4, 2 versus 5. Then 3 versus 4, 3 versus 5, 4 versus 5. Okay. Or in other words, you're going to consider k into k minus 1 by 2 binary discriminant functions for every possible pair of classes. Okay. So then you can just take majority voting for classification. Then you do majority voting. Okay. So it so happens that this classifier also has a loophole. Okay. So let's consider again the 3-class scenario. So now first we have, let's say this is a classifier which says C1 versus C2. Okay. So when you have 3 classes, C1, C2, C3, so how many classifiers you will have? There will be one classifier for C1 versus C2. Then you will have another classifier for C2 versus C3. Then you need one more classifier for C1 versus C3. I think this covers all possible pairs, right? So this is for C1 versus C2. Okay. Now let us say I have another classifier like this, which is for C2 versus C3. Okay. Now let's say I have another classifier which is C1 versus C3. Okay. Now you can see the problem, right? So let me. Okay. So now you can see that. So this is all considered as class 1, right? Now, similarly, I think this is considered as class 2. This is considered as class 3, but you have this region. Okay, so which is classified as, I think, all the 3 classes. Right? So this class, for this particular region, all the 3 classifiers says, oh, this is class 1, this is class 2, this is class 3. So this is the region of uncertainty, like when you have one versus rest classifier. Okay. Now this brings us to the question, like, can we come up with a classifier where there is no confusion, like where there is no doubt about which is the correct class? Okay. So that is our final approach. Okay. So the third approach is to use the idea of just one discriminant instead of k discriminants or k into k minus 1 by 2. Okay, so we're going to consider only one k class discriminant. Okay, which is going to have k linear functions of the form yk of x is equal to wk transpose x plus wk0. Okay, so we're going to consider only k linear functions. Okay, and we're going to say that if yk of x is greater than yj of x for all j not equal to k, then x belongs to class ck. So this is not one versus one comparison, like, or one versus rest comparison. Here I just say, okay, if you have k classes, give me k different numbers. Now whatever number is the highest, that is my class. Is that clear? Now, so how would the decision boundary between ck and cj look like? So what would be the point where 2 classes meet, ck and cj? Anyone? Sorry, what?
Why is it called 0?
No, we are not in two-class setting. So we have k classes, and you have k different y functions. Now, what is the decision boundary between ck and ck? So when would you say something is class k instead of class j? Look at the equation. So you'll say something is class k instead of class j if the y value of class k is greater than y value of class j, right? So the decision boundary is going to be the place where both the classes have same y value. Or in other words, yk of x is going to be yj of x. Okay? Or wkx plus wk0 is going to be wjx plus wj0. Now I can write this as wk minus wj transpose x plus wk0 minus wj0 is equal to 0. Okay. Now, this decision boundary looks like w transpose x plus w0 is equal to 0, right? So all the geometric intuitions that we discussed for one two-class problem, you can just apply the same properties even for this setup. Okay. Now, what is interesting about this particular setup is that it doesn't have any of the uncertain regions like 1 versus 1 or 1 versus rest. Okay. So this is going to have a perfect boundary. In other words, if you have three classes, the boundary is going to look something like this. Okay. So you will have, or let's say Ri, Rj, Rk, right? So if you have three classes I, J, K, your boundary is going to be very neat like this instead of 1 versus 1 or 1 versus rest. Okay. Now I can in fact prove this. This is a very simple thing. Okay. So the decision regions of such discriminants, okay, are always singly connected and convex. Okay. So what do I mean by singly connected? Like they are not going to be in different regions. It's going to be in one place together for one class. Okay. And it is convex in the sense you take any 2 points. Okay. So now any point that is in between, right? So it's going to have the same class. Is that clear? So now any point, let's just say this is xa, this is xb, and let's say this is x hat, something in between. Okay. Now any point x hat that lies on the line connecting xa and xb, right? Now I can just write this point x hat to be some lambda times xa plus 1 minus lambda times xb for some lambda between 0 to 1, right? So that is any point in between xa and xb. So now yk of x hat is going to be lambda times yk of xa plus 1 minus lambda times yk of xb. Okay, so this is by linearity of discriminant functions are linear, which means this equation is true. Okay, now we know that yk of xa is greater than yj of xa because we are in region k, right? So it has to be greater than yj of xa. And also yk of xb is greater than yj of xb for all j not equal to k. Okay, so this is because we are in region k, right? Now this also means that yk of x hat is greater than yj of x hat for all j not equal to k, which means x hat actually belongs to rk. Okay, so what I have proved here is you give me any 2 points, anything which lies in between is going to be in the same class. Okay, so there is no confusion. Like you take this point and this point, everything inside is in the same class. So you will not find any region in between which is in a different class. Okay, so which means that you can actually have this nice function. Is that clear? Okay. Okay, I think we discussed a lot of properties. So now let's start with the simplest possible algorithm, okay, which is something that we have already seen before, which is the idea of least squares. Okay, now let's talk about least squares for classification. Okay, so now if you think about one of the previous lectures where I said, oh, we want to solve classification, but we can just take the linear model from the linear regression and use it for classification, right? Like, so in that time, it sounded like a heuristic. So now we will see why it is actually a good idea to do. Okay, so we are going to consider a classification problem. Okay, where there are k classes. Okay, and I'm going to do one of k binary encoding or binary coding scheme. Okay, now we know that the least square is trying to approximate E of t given x. Right? We already know that. Now, if you think about the 1 of k encoding, so the 1 of k encoding, like when you have multiple, for example, let's say 1 0 0 0 0, right? Now, this 1 of k encoding is also trying to model probability of ck given x. Right? That is the probabilistic interpretation of 1 of k. So, in that sense, it actually makes sense to use least square. So, least square is trying to model E of t given x, and 1 of k encoding is also trying to model probability of ck given x. So, they are both same. So, it is a good idea to use least squares, right? However, there is a problem. So, what is the problem? So, what is the problem in using least squares for classification with k classes? Anyone? Anyone in the chat or here? So what's the problem?
A lot decimal points.
What do you mean by decimal points?
Your final goal, as you said, like.
Okay, so you're trying to model P of ck given x, right? But you're using linear regression. So is there anything in the linear regression equation which enforces the output to be probability values? No. So what is the range of your output in linear regression? Sorry?
Real value.
Real value. It could be anything, right? Like your linear regression could just say P of the first term is -5 or it is +20. Okay. Now, the numbers are not going to be in the range of 0 to 1, right? However, there is actually a very interesting property of linear equations. Okay. Now, if your training set satisfies certain constraint, like something like this, okay, then the linear model will also satisfy the same constraint. So it will also have AT of y of x plus b is equal to 0. Okay. Now, if you think about the constraint in 1 of k encoding, you take any 1 of k, the sum of all the values is going to be 1, right? So you consider this, or you consider 0 1 0 0 0. Okay. all your outputs have this constraint that their sum is going to be 1. Now you can try using linear regression for classification, okay, offline after the class, and you will see that the output y functions, right? So they will always sum to 1. However, the numbers could be positive, negative, so they don't have the probabilistic interpretation, but it is just a nice observation that they are going to sum to 1. Okay, now it's all fine, but as you can imagine, this is going to be the worst classification algorithm, right? So like we are going to design better algorithms in the next few weeks, but this is really the basic classification algorithm. So this algorithm has a lot of issues, okay? So for example, least squares lack robustness to outliers. Okay, so what do I mean by that? So for example, let's consider I have a problem like this. Okay, I find a least square solution. In this case, this is a linearly separable problem. So I can actually solve this problem very easily. So this would be my solution. Okay, now if I just take this, okay, maybe I'll put it here. Okay, if I just take the same data set and add some extra circles here. Okay. Now, can someone tell me what will happen to the decision boundary? It becomes closer to this thing, right? So your decision boundary will become something like this, for example. Okay. Or in other words, whenever you have, often in real life, your data set, you're going to have outliers. Okay. Like for example, there could be one day when machines malfunction. Like your temperature recording machine might give you very high temperature, okay, but we know it's an error in the data, right? So like there's going to be a lot of outliers in your data set. Like so for example, sometimes there might be a misclassification. For example, let's say you're using humans to label images. Okay, somebody, instead of typing this is a dog for a dog image, let's say you have a drop box to pick. So they might have intended to pick a dog, okay, but accidentally they would have picked, let's say, lion. You have a dog picture which is classified as lion. Now this is clearly an outlier, right? Like it's a wrong classification, like somebody did it as a mistake, but your linear model is going to trust every single example and give weightage to those examples, which means you're going to make like terrible loss. Is that clear? So the other problem that sum of square error has is like kind of penalizes examples even if they are too correct. So the whole idea of linear regression is to fit the curve, right? So you expect the data points to be close to the curve. That is what least square is trying to do, right? So now in classification, it doesn't make sense. In classification, I don't want the examples to be close to my decision boundary. It's perfectly okay. Like for example, like what I'm looking for is a classifier which, even if I have something like this, still tell me that this is the right line, right? The least square doesn't achieve this objective, because for least square, it kind of matters where your data points are, because the function is given by y of x minus f of x minus w, the whole square, right? So the far away the data point goes, you are squaring the loss. So even if it is correct example, like you're going to have non-zero loss, which doesn't make sense, right? Well, also in general, like this doesn't work for a lot of problems. Like I can give you one practical example. So here is a 3-class problem where I'm trying to do linear discriminant model that we discussed, right? So in this case, you can see that it couldn't model the green curve at all, right? Like so, it makes a lot of mistakes. But this is all, if you think about it, like it's kind of easy problem because you can just draw you can just draw one line here and one line here. You're going to get a very good classifier, right? But the problem is the simple model that we have cannot draw these lines. Like, so it can only draw something like this, right? So linear models are not always good. So they are very limited, which means we should consider something more complex than linear models, right? Like, so I think so far in this course, like we spent too much time on linear models, right? Like, so now we will start thinking about how can we do better than linear models. Okay, now we are not going to directly jump to nonlinear models. Okay, so in one end we have linear models, which has very limited functionality because they can only model like lines or hyperplanes. In the other end, we have nonlinear models. Okay, but in the next week's lecture, like we will go one step towards nonlinear model. Okay, so we're going to discuss what I'm going to call next week as generalized linear models. Okay, now the generalized linear models are going to have nonlinear functions, okay, unlike linear models, but their decision boundaries are still going to be linear. Why is that an advantage? So probably I don't want to start something when there is only 5 minutes, so we can actually finish 5 minutes early today. Like, so hopefully this will reset the cycle, like the clock. So next week we will see one whole topic. Okay, so we're going to talk about generalized linear models, like which will have linear decision boundaries but non-linear functions next week. So we'll stop here. Any questions? Well, we have 5 minutes, so you don't need to leave immediately. Any questions? Well, you can leave, like, but if you have any questions.